We just launched a brand new e-commerce platform. The marketing team is thrilled, but suddenly the server starts screaming. Within seconds, bots are brute forcing our admin logins, our endpoints are flooded with fake registration requests. Some guy just bought 16 laptops when we only had 10 in stock. And to top it all off, an attacker is actively dumping our entire product database just by typing a few characters into the search bar. Absolute chaos. Fortunately, this didn't happen to a real business. It was just a regular Tuesday for us in our security lab. Hi everyone, my name is Jin Kai, and welcome to our presentation. For this project, we built a fully functional e-commerce system so we could tear it down, and then learn how to build it back up securely. In this video, we will show you exactly how we executed 5 major threats: an application layer DDoS, brute force logins, SQL injection, an oversell race condition, and cookie falsification. But we didn't just break things. After each attack, we will show you how we use control, like rate limiting filters, parameterized queries, and atomic database updates to stop the attackers. Let's dive into the war room. Here is what the system looks like.
Hi, my name and my student ID are shown below. In this project, I was mainly responsible for the implementation of the core business logic, the monitoring pipeline, and the defender-side architecture, and attack 1. Before going into the details, I will briefly introduce the overall system architecture. The system uses Spring Boot as the business service, Prometheus for metric collection, and Grafana for monitoring visualization, all running locally through Docker. Next, I will use attack 1, namely brute force login, to demonstrate how the previous 3 parts work together. Moving to the dashboard, if you look at the top right panel, rate limit and the blacklist events, you can see there is basically no effective data. This indicates that attack traffic was not handled at the filter layer. Next, I will show the safe mode. Here, the same attack script, the same threading model, and the same attack pace are used, with the only difference being that is the target endpoint is switched to /user/login-safe. The most important part is the top right panel. We can see that the rate limit and blacklist relating events rise rapidly, with the blacklist hit curve being especially obvious. This indicates that a large number of requests have already triggered the rate limiting and blacklist mechanisms in the ingress layer. If we now look at the bottom left panel, brute force signals, we can see that compared with vulnerable mode, the signals related to login failure and login success remain almost at 0. This means that most brute force guessing requests never truly enter the password validation path. In other words, the core value of safe mode is not to stop the attacker from sending request, but to make the attack request lose the chance to enter the authentication logic as early as possible.
Hello everyone, I'm Join Zhang. I'm responsible for the 2 attacks in our project, DDoS attack and SQL injection attack. First, for the DDoS test, I'm using float script against the registration and export endpoints. It shows in the result shows in this window. As the vulnerable mode, the server keeps processing the request, so the attack creates the backend load and network traffic. It can show it as the curves in Grafana. And also in the safe mode, the system applies rate limiting and temporary blacklisting, so the requests are rejected by HTTP 429. Second, for the SQL injections, I compare normal input with malicious payload on the search endpoint. Under the normal input, both vulnerable and safe modes returns the same result. But when I inject into the keyword fields, the vulnerable endpoints returns more rows than before, and the safe endpoints does not show this effect because it used a parameterized request to block the SQL injection.
Here comes to my part. My name is Xiaojue Feng. I'll introduce you the last 2 attacks. First, oversell attack. An oversell attack occurs when a system processes more orders than available inventory, typically caused by a race condition during high concurrency traffic. In our system, the safe version checks before actions, while the vulnerable version does not follow this pattern. You can see the outputs like this. We started with a stock of 10. 10 users attacked simultaneously, each requesting 8 units. The vulnerable system failed, as it allows 2 successful orders for a total of 16 units. However, once we switched to the safe mode, only 1 order succeeded. It matches our expected result. Now let's move on to the second attack. Cookie falsification. This happens when an attacker intercepts a sensitive cookie or tries to bypass security by forging identity headers. Now look at our test results. We passed all the 3 checks. This output proves that, regardless of the attack vector chosen, our defense mechanisms remain robust and cannot be easily bypassed. That's all. Thank you for your attention.